Hey everyone, Tyler Case here, meteorology senior at Rutgers University. So the most common question I get as a meteorologist is what goes into a forecast? What are the sort of things you look at? So I'm going to kind of try and answer this question. So if you ever wanted to make your own forecast, so this is a website called AccuWeather. So this model page you actually do have to pay for. However, most of this information is available for free. So this is looking at a weather forecast model, which a model is basically it's a software program. It's run on a huge supercomputer, sometimes combinations of multiple supercomputers, and they will process weather data and spit out an output that will allow us meteorologists to look at it and sort of see what the computers think are going to happen, and then we'll offer our own interpolation into that. So as I said, AccuWeather is a site you can pay for, but this is called the GFS model, or the Global Forecast System. It's an American-made model. And it goes out pretty far. So you can see this again is a site you can pay for, but you can find all of this information also at the National Center of Atmospheric Research, which is NCAR for short. They're run out of Boulder, Colorado, and they run this website here where you can see, you can just go to weather.rap.ucar.edu, and you can click on GFS, click loop all times, and pick whatever you want to look at. So let's say I want to look at precipitation, and it'll load this map, and it'll run it out for you. And you can see this is what the model is forecasting. But I'm going to use AccuWeather for now because I can sort of easier diagnose what's going on here. So that's what I like about this site. So this is a 300 millibar map. Now a millibar is a unit of pressure. The surface pressure on the Earth, on average, is around 1,013 millibars. So usually pressure decreases as you go up in altitude. So 300 millibars is towards the top of the atmosphere, and this is usually around where we see the jet stream. So that's what this map is showing. So this is 6 Zulu time. So Zulu is Greenwich Mean Time, or GMT as you'll hear it referred to. You also sometimes hear it referred to as UTC. What that is that's a standard time that is used throughout the meteorological community and even the aviation community all over the world. And what that allows us to do is easily convert from one set of time to another. So all models will be forecast in Zulu time, so they'll have that Z time, and then you can easily convert to whatever time zone you are in. So on the East Coast, right now we're on daylight savings time, we are Z minus 4, or Zulu minus 4, meaning we are 4 hours behind Greenwich Mean Time. So 6Z would actually be 2 a.m. Eastern Standard Time, and then that would actually be 11 p.m. West Coast time. So you can sort of do the math there and figure out where you are. So right now we are looking at 2 a.m. on Thursday, which is today. So this map's showing the jet stream. The colors are showing the speed of the wind. And these little barbs here are showing the direction. And they also have these little ticks on them that allow you to see how fast the wind is blowing. So a little pennant, like the triangle, is 50 knots, and then each barb is 10. So right here over Wyoming, this is a 70 knot wind. And you can also see the contours. The color contours are helping you sort of infer that. This is pointing where the wind is coming from. So right here, the wind is coming from the northwest, and over here over New Jersey, you have the wind coming from the southwest. So this little dip here, so you can see it comes down, the winds come down over Nebraska, down over Missouri, up across Kentucky, and up into the northeast. So this is called a trough right here. And this is sort of what can allow for some cold weather outbreaks, because this air can now just leak down from Canada. What this can also do, and this is called a ridge over here on the other side over California, and this can block weather systems from coming in. So any weather system out here over the Pacific is going to get lifted along that ridge and miss California. And that's part of the reason why they're in such a bad drought over there, is they've sort of had consistent high pressure and some ridges in that area that have just pushed all the systems that are coming in off the Pacific out of the way. So I'd expect drier, warmer weather down here, because you can get air off the ocean up from Mexico. It can just leak into the area. But I expect cooler weather over here over Minnesota, Wisconsin, down into Michigan, maybe even Indiana, Ohio, and parts of western Pennsylvania. New Jersey, we're in the middle of a jet streak. So a jet streak here is just an area of higher wind speeds in the jet stream. So you can see this little pink contour here. This is a jet streak right here. We are in what's referred to as a left entrance region. So air that's entering a jet is in an entrance region. So you can see the air over New Jersey is entering a jet. And moreover, it's entering the jet on the left side of the jet, which makes it a left entrance region. There's also left and right exit regions. So that would be up here towards like Caribou, Maine. That's a left exit region. Right exit region would be over Canada over here, and out over the Pacific would be the Atlantic would be a right entrance region. Those can be used to forecast precip generally. So generally, right entrance and left exit, you would expect upward vertical motion for some very complicated reasons that I'm not going to go into, and that can lead to some precipitation. So we're looking at downward vertical motion here over New Jersey because we're in a left exit, and that would allow me to assume clear weather, which if you look outside this morning, it's pretty clear right now. One level down, so this is 500 millibars. So this is sort of the mid-range of the atmosphere. And what we generally plot here is wind speeds, so you can see the barbs again here showing wind speeds. Notice they're a little slower because there's a lot more friction closer to the ground that slows those winds down. If we look at this, these color contours, those are showing vorticity. So vorticity is the tendency of a fluid to swirl. So the atmosphere is a fluid. It likes to move around. And moreover, it likes to swirl. And the direction of which it swirls can lead us to infer certain things. So these red colors are showing high cyclonic vorticity, which means it is swirling like a cyclone, which is counterclockwise in the northern hemisphere. Those tend to lead generally. Now there's a lot of contributing factors here to storms. So you could expect some storms here over Virginia and West Virginia if you were just looking at vorticity. But again, there's a lot of things that correspond to that. There's also advection of vorticity by the wind. So advection is just the movement of some meteorological quantity from one place to another by the wind. So the winds are out of the south here, so this cyclonic vorticity is actually being advected into parts of northern New Jersey. So you could expect some upward vertical motion in there. And then when we can go down a level, we can actually look at upward vertical motion. So this is the 0-hour analysis for the GFS, and you can see, again, a little bit of upward vertical motion in northern New Jersey, like I said, but mainly a zero contour here, meaning it's just kind of there's not much lift going on here, which would lead me to expect clear weather if we were looking at nothing else. Another thing we look at is moisture content. So this is showing RH is relative humidity. So this is basically the amount of moisture in the air. So all these brown contours, that's dry air, and you need moisture to create storms and rain showers. Up over here, over New York and up into Maine, parts of Vermont and New Hampshire and even New Jersey, excuse me, we're seeing these green contours, which mean there's more moisture in the air. So there's air readily available. Now, if we reach 100% humidity, that means the temperature and the temperature at which dew forms are at the same. So when the humidity reaches 100%, that's when we would usually get dew. Like when you go out in the mornings and your grass is wet and it hasn't rained, that's what that is. You can also get fog when that happens, and that's just the atmosphere can't hold, or the air near the surface can't hold all of the water vapor that's there, so it condenses out, and that's when you get fog. So you can see kind of high, and then obviously the humidity, that's what keeps it hot and muggy over the summer, and nobody likes that. So now I'm actually going to go forward so we can look at some rain forecasts. So as I said, mainly downward vertical motion here. You can see New Jersey's looking pretty clear, as is most of the United States. Now there is this system starting to push in to the northwest, so you could expect some rain here. This is actually a front, I'm guessing, looking at these contours here, dipping into the northwest. You can also see that front that brought us some rain yesterday, well off the coast. So this is, remember, in that right entrance, so you're getting some contributing upward vertical motion, and that's why you're seeing some rainfall here. Now I can actually drag this out, and just basically what we'll do when we forecast is we'll just look at each progression of these and see, you know, what's happening. And this allows to get us to get a little deeper into what's happening. Another thing we can look at is called Model Output Statistics, or MOS, as we refer to it as MOS. So you can just Google search National Weather Service MOS. This is the URL up here. You can see I've selected Caribou, Maine. That's a city that I'm forecasting for in a challenge right now with the meteorology department. If I click Submit, you can see I get all this text data. And this is basically just numerical output of the map that we just looked at over here. It's the same stuff. This is just the numbers. And this allows us to sort of closely see what they're forecasting. So you can see these are the hours of the forecast. So this is 12 Zulu, and this is 6 Zulu. So you can see here's what we were looking at. Actually, what we were looking at before is not on here, but this is 6 hours after that. You can see the new temperature. This is going to be the high for the day. This model, the GFS, is looking at a high of 48, but going down into the 20s tonight up there in Caribou. This is the NAM, or the North American model. It's another model. It doesn't go out as far, but it's generally a little bit more accurate in terms of short-term weather forecasting. So you can see they're going to a high of 49, low of 26 again. So this is just a different way that we can look at it. You can see they have cloud cover here, so these are overcast skies. Whenever you have clouds, you're looking at usually cooler temperatures during the day, but warmer temperatures at night because the radiation gets trapped as it tries to leave, and then it's just reflected off the tops of the clouds by the sun during the day. This is just another model, the HER, as it's called, or the High Resolution Rapid Refresh. This is actually just the rapid refresh, but if I go to HER, oops, this is the High Resolution Rapid Refresh. This is just a different model that you can look at. So these are some of the things that we look at as we record, or as we forecast. And if you guys have any questions, please let me know. I'm happy to answer them. Just go ahead and comment on this, and thanks for watching.